We all think we know what a chemical bond is. It's just that simple line we draw between two atoms, right? But what if I told you there's a whole hidden world inside that little line? A world of waves, energies, and, well, some really surprising magnetic properties. Today, we're going to pull back the curtain on that hidden life using a seriously powerful idea called molecular orbital theory.
So here's the plan. We're going to start with a pretty weird secret about the oxygen we're all breathing right now. That'll lead us to meet the theory that can actually solve the puzzle. Then, we'll build some bonds from the ground up, run into a tricky but super interesting complication, and then finally, we get to solve that oxygen mystery once and for all. After that, we'll even see how this all applies to more complex molecules. Let's get into it.
All right. First up, let's talk about a molecule we all depend on every single second of our lives, good old O2. Now, this is probably how you remember oxygen from chemistry class. It's the classic Lewis dot structure, super neat, super tidy. You can see that double bond holding the two oxygen atoms together, and if you count them up, all the electrons are nicely paired off. Seems straightforward, doesn't it? Well, here's where it gets interesting. That simple drawing, it's actually wrong. Dead wrong about a really important detail. See, experiments show that if you pour liquid oxygen near a strong magnet, the oxygen sticks to it. It's paramagnetic. And that can only happen if the molecule has unpaired electrons. So that neat, tidy picture we all learned, yeah, it's failed us. To figure out what's really going on, we need a better tool. We need a more powerful way of thinking. And that's where our hero comes in, molecular orbital theory. The whole idea behind this is pretty revolutionary. It says that when atoms join up to form a molecule, their individual electron orbitals, those fuzzy clouds where electrons live, don't just stay separate. They actually merge, they overlap, and they create brand new orbitals that belong to the entire molecule. It's like they're pooling their resources to create a whole new set of electron real estate. And they can combine in two main ways. On one hand, you can get what's called constructive overlap. The electron waves add up, creating a stable, low-energy bonding orbital. This is the glue that holds the atoms together. But they can also combine destructively. The waves cancel each other out right in the middle, and that creates a high-energy, unstable anti-bonding orbital that actually tries to push the atoms apart. The real story of any bond is the cosmic tug-of-war between these two. Okay. Theory is great, but let's see how this actually works. We'll start with the simplest possible molecule, hydrogen, H2. Now, this new way of thinking gives us a really cool tool called bond order. It's a simple little formula that tells us how strong the bond is. Is it a single, double, or triple bond? You just take the number of electrons in those stable bonding orbitals, subtract the number of electrons in the unstable anti-bonding ones, and then divide the whole thing by 2. That's it. So for our hydrogen molecule, each atom brings one electron to the party. Both of those electrons are going to jump into that cozy, low-energy bonding orbital. So our math is simple. 2 bonding electrons minus 0 anti-bonding electrons divided by 2, and that gives us a bond order of 1. And what do you know? That's exactly what we expect, a single bond. The theory works. Okay, that was pretty clean. But of course, as we move to bigger atoms with more electrons, things get a little spicier. Let's talk about a fascinating little twist in the story called sp mixing. So the idea here is that for some atoms, the energy levels of their 2s and 2p orbitals are really, really close together. They're so close that they actually start to interfere with each other or mix. You can think of it like 2 guitar strings vibrating at almost the same frequency. They create a weird new sound. In atoms, this mixing literally shuffles the energy levels of the resulting molecular orbitals. This tiny effect has massive consequences. And you can see the result right here. Just look at the diagram on the left. That's for molecules like nitrogen, where you have a lot of this sp mixing. Notice how the pi bonding orbitals are actually lower in energy than the sigma one. Now look at the diagram on the right for oxygen, where there's almost no mixing. The order is completely flipped. The sigma orbital is now the lower energy one. It's wild. Same building blocks, but a totally different set of rules. So what's the deciding factor? It's all about that energy gap between the original s and p orbitals in the atom. In something like nitrogen, that gap is pretty small, so you get a lot of mixing. But as you move across the periodic table to oxygen, that energy gap gets bigger and the mixing effect just fades away. And this one little detail is the key to solving our entire oxygen mystery. All right, the moment of truth. We've got our tools, we know about bonding and antibonding orbitals, and we know that for oxygen, we need to use the diagram that has no sp mixing. Let's go back to that original problem. And here it is, the big reveal. Each oxygen atom has 6 valence electrons, so that's 12 total for the molecule. We start filling them in from the bottom up, following the rules. And now, look what happens with the very last 2 electrons. They land in 2 separate antibonding orbitals that have the exact same energy. Now, just like people getting on a mostly empty bus, they're not going to sit next to each other if they don't have to. Each one takes its own seat. They stay unpaired.
This one diagram tells us everything we need to know. We do our bond order calculation, 8 bonding electrons minus 4 antibonding divided by 2, and we get a bond order of 2. So it correctly predicts the double bond, just like the old Lewis structure did. But and this is the amazing part, it also tells us there are 2 unpaired electrons, and that means O2 has to be paramagnetic. Mystery solved.
And this isn't just some lucky guess. This theory has incredible predictive power. Take a look at this graph. It shows the actual measured bond distance for a whole series of molecules, and the trend is just beautiful. As the bond order we calculate goes up, the bonds get shorter and stronger. Then, as we start filling up those nasty antibonding orbitals, the bond order goes down, and the bonds get longer and weaker. The pattern is predicted perfectly by the theory. It's stunning. Okay, for our last trick, let's see what happens when the theory has to deal with molecules made of 2 different kinds of atoms. For these molecules, what we call heteronuclear molecules, there's a new wrinkle. The atomic orbitals of the 2 different atoms don't start at the same energy level. You can see here, fluorine is way more electronegative. It's an electron hog. So its orbitals are at a much lower energy to begin with because it holds on to its electrons so much more tightly than hydrogen does. So when these 2 atoms combine, this starting energy difference means you get an asymmetrical molecular orbital diagram. The new bonding orbital that forms is much closer in energy to fluorine's original orbitals. And that means the electrons in the bond are going to spend way more of their time hanging out around the fluorine atom. And get this, that is the fundamental origin of bond polarity. This theory doesn't just predict bonds, it predicts their entire character. So let's wrap this up. What's the big takeaway? We started with a simple picture of a bond, the Lewis structure, and saw that it just couldn't explain a basic physical property of oxygen. But then molecular orbital theory came along and gave us a much deeper, much richer story. It showed us how atomic orbitals literally merge to create new homes for electrons that span the whole molecule. And with that powerful idea, we can accurately predict bond strength, bond length, and even magnetism for all kinds of different molecules.
And that kind of leaves you with a bigger question, doesn't it? If a more powerful theory can reveal such a complex and hidden reality inside something we thought was as simple as a chemical bond, what other secrets are hiding all around us, just in plain sight, waiting for us to find the right way of looking at them?